Welcome to the Wednesday Lecture Organic Dorks. I'm going to review a little bit of what I did a chicken scratch lecture on my little whiteboard program, and then we're going to launch into a couple of just different ways of seeing this like acid and base conditions in enolate reactions. Nothing too major. As I said, we're hopefully going to kind of take our foot off the gas a little bit in preparation for that exam that you guys have coming up on Friday and Saturday. So one of the things we talked about was this idea of an alpha substitution. These slides, as always, are available just underneath where you're finding this lecture video, by the way. And hopefully you got enough from my whiteboard to notice that we formed this thing called an enolate in basic conditions, and then that thing can then do some sort of electrophilic addition, or ultimately a substitution here. And that electrophile is almost always going to be, for us, either a ketone and aldehyde or some sort of carboxylic acid derivative. The two reactions I have for you today are a little bit more simple because you were just adding one or two little atoms, halogens and such. But a couple of things to keep in mind, right? Alpha substitution, we're going to substitute something that is on a carbon right next to that carbonyl carbon. And at least in base, it occurs through an enolate ion. And one of the things we're going to see today is an acidic mechanism. And we'll see that that actually goes through an enol. And just in a little bit more detail, one of the things I talked about was the fact that when we add aldehydes and ketones, we're essentially doing alpha substitution chemistry followed by some sort of kind of more normal looking carbonyl addition reaction. So there's one of those. And then when we take a look at what this thing does with a typical carboxylic acid derivative, once again, we see that nucleophilic substitution that we know and love from all of our derivatives. One of the first things that we typically learn when we study some sort of new functional group is how to put halogens in. Keep in mind, halogens are kind of the mover and the shaker in terms of organic chemists. And there are kind of the equivalent in biological systems, certainly not halogens, but they also have certain groups that kind of do this. So it's really useful to see these halogenation reactions, even if you don't plan on actually doing any laboratory organic chemistry. So here is a great example of a base catalyzed process. We're going to just kind of see the mechanism of this sucker in just a second. Turns out ketones and aldehydes, anything with an alpha carbon, we can have that OH come in, pop that hydrogen off, and then just like we've seen in, well, geez, way back in the days of like additions to alkenes, these halogens can serve as electrophiles. So it turns out that under basic conditions, you can actually put a substitute a halogen for that hydrogen that used to be there. The curious thing about these reactions is that the second that you do that, because that increases the acidity of all the different hydrogens, right? We talked about the fact that halogens tend to increase acidity through stabilization of the conjugate base. It turns out that it's very easy once you put one halogen on to put more halogens on, and that leads to a couple of different reaction types. There is the mechanism that shouldn't be too surprising, right? We've got that OH coming in, ripping off the hydrogen, forming an enolate. And once again, you'll notice that most of the time we'll see this in mechanisms. So instead of showing it like this, it's pretty common that you show this thing being the thing that attacks the electrophile, in which case a lone pair of electrons comes down, attacks the carbon, which forces this guy out, and then there's an attack of a halogen. So here is an example of what happens if there are multiple halogens, and you kind of keep going, and you end up pretty much taking every single H that is on there and turning it into a halogen. And I just kind of mentioned that, the fact that the second you put in one halogen, you're more likely to get a second, at least under basic conditions. It turns out this leads to a really popular question on the ACS to be asked about, which is called the Haloform reaction. This is something that methyl ketones undergo. And a methyl ketone, I think this is pretty obvious, but has a methyl group attached directly to the carbonyl. It turns out that you're going to replace every single one of those hydrogens through the mechanism we just looked at. And what happens later in the mechanism here, which we'll take a glance at now, I guess. So here is that kind of surprising part of the haloform reaction, is after you've actually gone through and replaced all of your hydrogens, you'll end up with actually having a direct attack of an OH group on the carbonyl, and this serves pretty much like a carboxylic acid derivative. And when that lone pair of electrons falls back down, you actually liberate this weird looking carbanion species. And ultimately, you end up with a carboxylic acid, or in the case of the basic conditions, a carboxylate ion. We don't care too much about this anymore. I guess it's somewhat useful to know that you can kind of clip off a CH3. I've never thought it was terribly interesting synthetically. But the one thing that is really popular on the ACS, if you do have to answer some sort of qualitative analysis question, for some reason this one still kind of sticks around. This is like an old-timey way, before we had NMRs and things like that, that you would do this reaction. And it turns out that the haloform will actually usually precipitate out and make this really bright color. So it's a pretty common thing that they'll talk about. They'll say that, this unknown compound gave a positive test with the haloform reaction or something of that extent. But it just means there's a methyl ketone there. I should mention at this point that I posted a whole bunch of slides. I'm really skipping through many of them, but if you're looking at kind of a more exhausting look at some of this chemistry, you can take a look at those slides. I'm just kind of limiting our look here. So one of the things I like about this slide is it directly is a perfect complement to the base catalyzed process. One of the things that is almost always the case is that our kind of source of weak acid here is going to be some sort of acetic acid. And then you notice Br2 once again, or Cl2, doesn't really matter. And one of the interesting things is with these reactions is generally you just end up with one halogen put on. Don't worry too much about the fact that this halogen gives two. Most of the time that we're having to predict products from this kind of thing, it's just one halogen. It's probably more interesting if we look at the mechanism of this sucker. So once again, you should know how to form this enol through some of the arrows that I showed you in Monday's lecture. So once you get to that enol, it's a pretty common step, right? Notice that this thing is really acting just like the enolate, right? Where there was a minus charge right here. And in fact, that's what I said. If you think that anything goes through an enol or an enolate, kind of think about it as in terms of this carbon having the minus charge. But ultimately, what we do is we end up with our product with an additional proton, and hey, how surprising, something comes in and deprotonates that thing with a positive charge. We end up with a product. So the general theme that anytime we do something in acid, we start and end with that proton going on and then coming off in the very last step kind of holds true in this case. Nothing too interesting. Oh, one of the things I did include in a lot of these slides, I threw in a couple of solved problems just to kind of help people with, I don't know, some of their homework problems. I'll try to, now that I've found these solved problems, I'll try to include these as a resource in a lot of your PowerPoint slides. This is just called Sean has a green screen and wanted to watch some Nazi faces melt up behind him. I'll see you Monday.